welcome to ePathshala lecture series in computer science, and this is a course in cloud computing. In this module, we will continue talking about cloud storage. Before we come to learning objective, in the last module we discussed about how the cloud is providing storage, a cloud service provider, how a service provider will be providing storage. As a part of that, we gave a few examples of practical cloud storage. Perhaps the most important cloud storage is being used by the distributed file systems, and the most popular of that is a file system called HDFS. In this module, we will talk about HDFS and how or why HDFS is very an integral part of cloud environment. So, our learning objectives today are: we will look at the HDFS design goal, and we will look at the various components of HDFS, architecture of HDFS, the new features that HDFS have come up with, and how to read and write data. Now, data is everywhere. A very large amount of data is available today, and therefore, we need to utilize this data. The utilization of the data happens or is done for the purpose of analytics. So, what is an analytics? Analytics helps us to take better decisions and to come up with or to predict a pattern or a behavior which will help us to improve the way we do business, or we do whatever mechanism that we follow. Now, it was there before also. Businesses used to happen based on their past experiences. So, how is it different today than what used to happen earlier on is what we wonder. So, how it is different today is the vast amount of data that has come. A very large amount of data is available today. We generate data using sensors, all our published books, our newspapers, we generate data through our mobile applications. Very many, all our social media generate a large amount of data. All these data have to be processed, and the data have to be processed very fast. The need to do it in a fast manner is what is different today than what used to be earlier on. So, what do we need to be able to do this is we need machines, fast computers which can process this large amount of data. So, what would be a fast computer? A computer which are very large computers, which means that we are talking about supercomputers like what is there in CERN, and we can use that kind of computers to process a very large amount of data fast and come up with some pattern or some analytics that is helpful for to decide how the business should behave tomorrow. But very large machines have their own disadvantages. The first being they are very expensive and not possible for everybody to build another CERN just like that. So, we ask, do we really need large machines? And if we look at the kind of calculations that we are doing using our large amount of data, we see that the calculations are very simple. They are not very complex, time consuming calculations. They are conceptually straightforward and simple calculations. So, where is the complexity then? If the calculations are simple, then simple desktops should be able to do that, but the data is so large that a simple desktop computer or a laptop computer is not possible to get the computation done in that. The other part is that we need it in time. Giving a desktop computer to process a terabyte of data, it will perhaps if we write the program properly, it will process the data and perhaps it will come up with the requisite analytics, but the amount of time it is going to take will be so large that the analytics will not be applicable or useful to the people. So, timely producing the processing of a very large data, churning of a very large data to come up with analytics is what is required. So, if large machines are expensive and their superpower in terms of complex calculations are not required, then what is our option? Can we really think of a better solution? The solution is to use commodity computers. So, commodity computers are the general workstations that we see everywhere. They are not very expensive and they are available. That is a resource that is easily available and easily procurable if the need is there. So, how many of these machines will be sufficient to churn this terabyte or petabyte of data? We actually need thousands, tens of thousands of such machines to be able to do that. So, we have this kind of machines, we also need a corresponding storage that should be attached to these processors to be able to make the data available as and when they need it. So, storage and processing power, and this can be done using a commodity machine only when we have a distributed storage system. So, so tens of thousands of nodes, say let us take an example of 10,000 nodes. Let us assume that there are 4 CPUs, 4 CPU node and there are 5 disks per node, then we have a very large distributed system which can store all our data, and each of the processors can process a part of the data, chunk of the data, and we can get the result. But what about failures? What about machines failing all the time? So, if we look at the statistics, Google says that approximately 1.7% of the time a commodity machine will fail, which means that given our 10,000 machines, there will be 850 failures per year, or approximately 2.33 failures per day. So, with this we need to go around replacing our disks all the time, and not only that, the problem of replacing is one part, the other part is the problem of losing the data. The data that will be stored in these disks will be lost, and we have to think of replacing that. So, this is a basic problem of using commodity machines. So, therefore, what is required is to obtain a platform or a framework which will take care of these failures. They will do things in the background. So, in the foreground the processing alone will run, in the background the failures should be taken care of, and the framework should make sure that all the machines are running parallelly and giving ultimately the overall result. The framework that we are talking about is called Hadoop. This is an Apache framework for doing big data analytics. So, let us look at what is Hadoop. Hadoop is an Apache project actually. It is an open source Java based distributed computing programming framework, and it supports a very large amount of data that can be processed or churned by using only commodity hardware. So, Hadoop has two parts. One is the map reduce, which is the processing, parallel processing in so many commodity hardware, and the other part is the HDFS, which is the distributed file system. It is called Hadoop distributed file system, and that will store the data, hold the data for the map reduce to continue. Typically, it is a cluster based system. As we will see later, we can do it in a single system also, but it works the best, the most efficiently if we have cluster in place, and it can handle this amount of unstructured data. Hadoop can handle both structured and unstructured data. That is another importance of having Hadoop using all commodity computers. So, if we have very large commodity computers, Hadoop will expect the computers to be arranged in racks, and it will provide a fault tolerant, always available and scalable framework in which analytics can be performed. Now, why Hadoop in cloud? This is a big data analytics mechanism. Why are we discussing in cloud? There are two things that can happen in a cloud. One is the service provider, the cloud service provider or CSPs may need to implement Hadoop as a background process using which they will deliver some service. If we take Amazon's EMR, which is the MapReduce program of Amazon, it uses it implements Hadoop in the background and will provide the Hadoop based mechanism. It has its computers computing in EC2 and its storage in S3. The other way of looking at Hadoop is offer Hadoop as a service. So, if a user gives their programs, the cloud service provider will run it in a Hadoop based, in a cloud based cluster of computers. So, what is the benefit of taking Hadoop as a service? It is very apparent how the benefit works. Essentially, it is a big data analytics which requires large processing. Many number of machines are required, and it should be able to churn a large amount of data set which should be made available. Now, the elasticity of Hadoop programs is very large. It may have a very large amount of data at some point in time and less amount of data at another point in time. So, we need an elastic system, and if we are running Hadoop in our in an organization, then it is not always possible to provide 10 more systems or 20 more systems at a quick notice, which is easily available in a cloud environment. So, that is why Hadoop is very much implementable in a cloud environment. In this module, we are not concerned about how the computing part works, because that largely is the taken care of by the user's program and the framework. We will look at how HDFS is made to sit in a cloud environment. So, what is HDFS? It is the Hadoop distributed file system. It is a Java based program which follows basically Google file system structure, and the large data can be stored. Basically, what is done in Hadoop is to split data into smaller blocks, and these blocks will be distributed across all the machines in a cluster. So, the blocks will be replicated for fault tolerance. The premise where we started this module is that there will be failures. The failures continue to happen. These are still commodities hardware. So, how Hadoop handles the failure is they inject a large amount of redundancy into the system. So, each block of data is replicated multiple times. Hadoop default mechanism is to replicate 3 times, but based on the requirement it can be less or more. These replicas will be stored in different nodes. Why different nodes? Because if one node fails, still the other node will be having the data, and therefore, thereby Hadoop ensures that it is a fault tolerant framework. So, what is the HDFS design goal? Are these that it is a very large distributed file system, huge number of nodes, huge number of files can be maintained there, and the philosophy behind Hadoop is that data movement is more costly, but computation movement is less costly. So, data will be stored based on the HDFS, it will store the data, and the computation will be taken from one place to the other, where to a node where the data exists as far as possible. That is how Hadoop works. It is a master slave design, which means that there is a master node and there will be worker nodes, and master node will control the worker nodes, and it is a simple coherency model. The Hadoop does not work for all kinds of programs. It works well for applications where there are less number of writes and more number of reads. So, it expects that there will be once the data is written, there will not be too many updates of the data, but there will be many reads, and reading the data is what essentially is supported in Hadoop. So, what are the components of Hadoop? One component is called the name node, and then there are data nodes and the secondary name node. The name node is the master. It controls the working of the data nodes, and data nodes are the workers which actually do the essential work. So, replication is the major magic of Hadoop. So, all the blocks of the file will be all the files will be divided into equal sized chunks. Typically, it is 128 MB, but it can be programmed according to the requirement, and the default replica placement strategy is one replica where the data has been submitted, that is the local node, another replica in a rack away from this data, not from in this rack, it is in another rack, and a third replica in the remote rack. So, one in a node, in a local node in the current rack, another in another rack, one data node, and the third is in that same rack in a third node. The idea behind this is that if this local data node fails, then the other rack's node will be working. If the rack fails, then also the other rack will be working. What is the replication policy? The replication policy works like this. So, this is our name node, and these are the racks, and the white ones are the data nodes. So, we have one name node and there are 4 racks in this example, and total 16 data nodes are there. These data nodes are inside the rack. Now, when some name node contains metadata, which is a data about data, and it stores all the block information and the replica information and where each of the replicas are stored in the data nodes. That complete information is stored with the name node. So, here in this example we see that the name node is storing this information, file name, the number of replications and the block IDs of the file, how many block IDs are there in that file. It stores this metadata, the name node, and this is an example where we see that first there is a path given for file 1, and the replication is there are 3 replications and 3 replication for each block, and there are 2 blocks, block number 1 and 3. So, if we assume that the local node is say 1, then block 1 will be put in node 1, and the other replication of block 1 will be away from this rack. So, it can be put in rack 2, node number 6, and rack 2, node number 7. Similarly, block 3 will be perhaps put in rack 2 in node number 5 and other 2 replicas in another rack. In another example, file 2, it has 3 blocks 2, 4 and 5, and it will be again put accordingly, one in one local node rack and the other 2 in the remote rack. So, this is the replication policy following which Hadoop maintains fault tolerance, HDFS maintains fault tolerance. Now, let us look at the architecture. what happens in the Hadoop architecture, this is the HDFS architecture, this is the name node and these are all the data nodes. Now, the secondary name node, the work of the secondary name node is to ensure checkpointing. We have learned in our during our theory part that checkpointing is a very important requirement of a distributed environment and hence of cloud. So, Hadoop HDFS employs checkpointing with the help of secondary name node and therefore, it tries to safeguard the name node failure. So, both the name node and the data nodes will be part of the cluster management, and if when a client wants to ask for a file, wants to read a file, now the file is split into blocks and these blocks are only known to the name node in the metadata. So, it will ask the name node where these blocks are there and which data nodes contain these. That block ID and the data node information will be sent back to the client and then client will contact the data nodes directly and they will get the data. So, they will get the chunks, the blocks and combining these blocks they will obtain the overall file. So, the problem is in the name node. The metadata that it contains has to be maintained by the name node completely. The namespace is a hierarchical file and directory environment and the metadata that it contains will be the list of files, the blocks for each of the files, because name node splits the data file into blocks and which data node contains which blocks, how many replications and the file attributes, the creation time, the replication factor, etc. It further maintains a transaction log to ensure fault tolerance, and this is the record of how many, what the files created, what the what have been deleted, how have been updated, etc. So, name node metadata is stored in two types of files. One is called the FS image and the other is called the edits. FS image is the overall state of the whole name node at any point in time. It is essentially, as the name suggests, it is a snapshot of the whole system. As we have learned earlier on, that snapshotting is a way of storing information, but it does not contain any data. It contains the current state of the name node environment, and edits is a log file which logs all the transactions. Using these two, name node and the secondary name node ensure that there is fault tolerance in HDFS environment. So, in case the name node crashes, then the file system cannot be used, because all the information about the file, how many blocks, where the blocks are, in what way the blocks should be connected, all these would be gone with the if the name node fails. So, what is the it is very important to ensure that name node is safe. It is not we should not allow name node to fail, but it is also a commodity hardware and it will fail. So, how to ensure that how do we handle name node failure? That is where our secondary name node comes in. The secondary name node will be running in the background and it will be monitoring and storing. It will create a necessary backup. So, it will take the snapshot and it will create the new snapshot of the environment. Let us look at how this happens. So, this is our primary name node and this is our secondary name node. The primary name node has two components, edits and FS image. So, some snapshot has been taken in FS image, and from next interaction onwards, the edits is storing the log file of what are the interactions that is happening. Now, when time comes for the secondary name node to interfere, the primary name node starts a new editors. So, editors, the earlier editors contains up to a certain point, FS image contains even before that the overall snapshot, and the primary name node starts a new editors which is called editors new. After this has been started, the FS image and the editors is sent to the secondary name node. So, secondary name node receives these two, and what the secondary name node does is it applies the editors transactions to the FS image to create an up to date FS image which is called the FS image checkpoint. This is the complete FS image of combining these two. So, whatever has happened till before this particular log has started will be present in the checkpoint, FS image checkpoint, and then it will send the new FS image checkpoint back to primary name node. Now, primary name node will now it has the new FS image, and it converts the editors new to the current editors and editors and FS image checkpoint to the current FS image, and it starts continues normally. If we see how the HDFS is working, there are two layers using which HDFS works. This is the name node, these are the data nodes. The first layer is the namespace. A very important part of the name node is to ensure the correctness of namespace. So, that is the first layer that Hadoop works with. The second layer is the block storage management. In that we have a block management part which is done by the name node. So, here are the work for this block management. It will give the data nodes the cluster membership, it will support all these block creation, all the block level operation, and will manage the replication and replica placement, and the storage which will physically take care of the reads and writes, because they contain the data. The data nodes contain the actual data. Name node is just having the metadata. Unfortunately, HDFS is not a perfect environment where it has its own limitations. Very poor performance, isolation is poor because there is only one namespace. Name node does not have high availability, and therefore, it causes a single point of failure, and it always needs the secondary name node to. There are two new features. One is called the name node high availability, and the other is called the HDFS federation. The high availability is where we have an active and a standby name node. So, there are two name nodes, and the data nodes, as usual there are multiple data nodes, and when the data node reports the block level information, it reports to both the name nodes, and the primary name node, active name node will create the editors and FS image, and the standby name node will use that to ensure that it is always available. So, whenever there is a problem with the active name node, the standby name node immediately takes over. This is a feature that has been incorporated in the new recent version of Hadoop called YARN, yet another resource negotiator. HDFS federation works like this. When there are so many data nodes having so many blocks, it runs multiple name nodes, and each of these name nodes has a block pool. Some blocks from each of the data nodes will be pulled for one. So, each name node will run a separate namespace, and these namespace will contain blocks from a subset of the data nodes or all the data nodes. This way, what will happen is the name node namespace will be isolated. Therefore, if we want to run a specific kind of applications, we can have an isolated namespace. What is the benefit of federation? Federation is the namespace scalability, because there are so many name nodes. So, therefore, horizontal scalability is there, performance is improved, and of course isolation is obtained. So, we will take a quick look at the read anatomy of the file of HDFS system, how the data flows. This is the client. The client also contains the two other modules which helps it to obtain the data. So, first the block information is obtained, and then when the block information is obtained by the client, it uses the FS data input stream to contact the corresponding data nodes and obtain the data. In case of write, which is the maybe the first time it is writing, it will have the write information, it will send the write information to the name node to create the blocks, and then it will send the data. The data is written in a pipeline manner. So, the data node will have this data, and then it will pass on to the next data node, and that data node will pass on to the third data node. So, this is how a write will happen in a HDFS. All the upcoming and large environments use Hadoop in a cloud to ensure data availability. To summarize this particular module, we looked at why Hadoop and data analytics, big data analytics is required, and then we justified why it is being done in cloud. We looked at the specific storage mechanism called Hadoop distributed file system, and we also justified why HDFS should be hosted in a cloud, and we looked at the architecture and the components of HDFS. We looked at the new features, which is the name node high availability and the HDFS federation. In the next class, we will start with what is known as a networking for cloud or cloud networking. These are our references. Thank you.